last class I ended with mode, right? And it was simple. It was very, very simple. The mode is the most frequent variable observed. And this is perfect for nominal kinds of data. So back to our example of eye color. It's perfect for eye color. Why? Because eye colors don't have values assigned to them. So you can't really find the mean color. Could you? Aaron, you want to say yes. How could you find the mean color?
The number of people that have it.
But how are you going to assign a value to blue or green or brown? Right? Because that's how we do means. We have to have numbers. Jake, do you think we can find a mean color?
I think so. I know there's a way to do it. I forget what it is. There's a way to do it.
It's like I heard one time there was a.
I did my problem stats class in high school.
Okay. Well, no, not the way I'm thinking about it. How can you find the mean color? Let me rephrase this. For the art people that are over in Edwards right now, can you quantify colors? There's an expression that I say sometimes. I have a PhD from a Big Ten university. I can quantify anything. I can quantify color. Because when you think about it, what is color? Color is the presence and absence of other colors. So how does a signal get beamed through the air to tell your TV what colors to project on the screen? Did you ever think of that? Like someday, honestly think about the science and the mathematics that goes behind taking an image and projecting it across the world virtually live. And then have that image appear on a relatively flat screen in your living room. I hate to break it to you, but there's math involved. So how do we do that? Well, we could quantify a color because colors can be measured for their traits. Anybody know what RGB stands for? Right? So every color is actually a mixture of these three colors. And if you ever do any web design, you can get the coastal shade of teal by putting in the right three colors for R, G, and B. So can you quantify colors? Absolutely. How would you find the average color? Well, if I had a paint store here, and I matched every single one of you had a paint that matches your eye color, I just mix all the paints together, and I'm going to get the average of them, right? By mixing the colors together. Or you can take something that you didn't think could be quantified, like color, and quantify it. So generally speaking, yes, mode is great for nominal data. But if you're creative and you think about how it is that you're representing that nominal data, you can transform it into a different form. And so with color, we use red, green, blue. For gender, could we transform gender from a dummy variable that is essentially two classifications into something that we could quantify in terms of a more continuous number? Well, you idiot, you asked the question, so you must know the answer. So I'll just sit here and be quiet. Yeah, we could, right? We could talk about gender as a representation of hormone levels. You could also go into the genetic code, and I know we're all taught the XY or the XX or XY, right, pairing. But it's got to be more complicated than that, right? That's genetics. It has to be really much more complicated than that. All right. So now that I've told you what these things are, how do we find them? That's simple. And some of these you don't even involve any math. Like, how do you find the mode? Well, that's easy. Look for the largest number on a frequency distribution table. That's all you do. So if you can take your data set and you can condense it down to a frequency distribution table, find the one that has the biggest number. I think Yogi Berra had a quote. It's like, you can find things by looking for them. Like, okay, Yogi, yeah, you can. Or you can see a lot by looking. He had some sort of Berra-ism like that. So how do you find the mode? Well, you don't actually find it. You just create a frequency distribution table, and then the act of doing that shows you what the mode is. Or if you've taken your data and condensed it in some other way, often look for a peak on something like a bar chart. Although I'm not going to teach any of you people how to do a bar chart. Bar charts. Or a histogram, or you look for the biggest slice on a pie chart. All right. So here's a bar chart. A crudely designed bar chart in Excel. What is the modal feeling towards candidate Barack Obama in 2007? What does that represent, though? Right, warm. What's the modal feeling towards Rudy Giuliani? So we look at Giuliani's bar chart, and we look for the highest one. And the modal feeling towards Giuliani is warm. And Hillary Clinton is warm. John Edwards is warm. John McCain is warm. That's the modal. How do I know that? It's the tallest one. Sometimes when people are doing bar charts, they want to show you the modal one right from the beginning. This is a bar chart that's pretty much sorted by the height of the bars. So you don't have to go looking. Right. Which has the most debt? The UK has the most debt. All right. I know that's not technically what I told you to look for, but the highest bar. All right. So that's the mode. How did we find the mode when we looked at our table? We looked for the highest percentage, and that was 85. That was the Hillary Clinton's modal score for her feeling thermometer. Okay. The median, this is the trickier one, because the median depends upon the actual number of observations, because we're looking for that middle point in the observation. I'll show you the math hard way, and then we'll do it and show you the intuitive, oh, you just look at the numbers, it's easy way. So if we have an odd number of observations, the median score is the n, where n equals number of observations, plus 1. So all you're doing is taking the odd number and making it even, and then dividing that by 2. Let's walk through an example. N plus 1 divided by 2. Here's a set of 7 numbers. N equals 7. 7 plus 1 is, thank you, almost had to break out my fingers and toes on that one, divided by 2. 8 by 2, 4. So I'm looking for the fourth score. 1, 2, 3, 4. So the median is 0. Right? Yeah, they got to be in order. So now we have to put these in order. 0. Cross that one out. What's next? 1. There's a 2. There's a 3, a 4, a 5, and an 8. 5 and 8. Which one's the fourth score? 1, 2, 3, 4. Median's 3. Told you, today's the last easy day. This is all high school stuff. I'm going to go home and teach it to Abby just to prove a point. Abby, you want to learn what Daddy taught his students today in college? I know you're bored with first grade already. Let's step it up a notch. Let's get you some credits. It's that simple. Or, because we know median is middle, there's 3 over here, there's 3 over here, it's the one in the middle. This is why I think math gets a bad rap, because I took as something as simple as finding the number in the middle and turned it into equation. Right? And this is where people get freaked out. It's because you have an equation that has letters in it. And you're like, n plus 1 divided by 2. Oh, I need to get Google open. Google, what is n? N is the 14th letter of the alphabet. Right? Damn it, Google. You didn't help me out. This is where people get freaked out for no good reason. It's very simple math. It's intuitive. But because we have to have sort of a universal language with math, we have to find the middle observation and transform it into an equation. And that's what it looks like. The n plus 1 divided by 2 score. Here's to prove my point. We're going to do the same thing, but we're going to do it with an even number of observations. Oh no, he made the equation bigger. Because now what we have to do is we have to find a number that's in between 2 other numbers. And we have to find out which of the 2 numbers we look in between. So really, to find those 2 numbers, we have the n divided by 2 score, and then the n divided by 2 then plus 1 score, and then we divide that by 2, and then we get the actual median. So let's do that. Here's a set of numbers. What should we do first? If we have to calculate a median, we should organize them, okay? Well, let's do that. What number comes first? Then 19. You sure? Okay, 24. Then 31. Okay, I've done that. Then what do I have to do now? I have to count them. Why do I have to count them? Because I need to know what n equals. What does n equal? 6. N equals 6. Oh, I have to do the middle thing. All right? So what is the median? 6 divided by 2 is, what's the third score? 1, 2, 3, 24. n divided by 2, which we already know is 6 divided by 2, which is 3, plus 1ths score. So what's the fourth score? 1, 2, 3, 4. 24 plus 31 divided by 2. 24 and 31 is, divided by 2 is 27.5. So what is the median of this set of numbers? 27.5. How did I get that? I looked for the middle of the data set. This is the middle, right? That's better. And now I need to find the middle of those two numbers. So what is the middle between 24 and 31? It's easy. You just take the average of them. This is not hard. This is annoying because, again, you're taking something and converting it into math. Because let's be honest, we're not going to always have data sets that are 6. Okay. How many observations did we have in the Hillary Clinton feeling thermometer? 2,306. Are you going to write out all two? No, you're not going to do that, right? But let's say if you were trying to program a computer to go through all 2,306 observations, you might want to find a way to tell the computer how to do that. So again, you have to take something that is intuitive and translate it into a universal language. So if we were to crack open Stata and look at the computer code that we use to compute a median, what do you think one of the first things that the computer would do to our data? Okay, it would organize it how? So it might sort it, okay. What else would it have to do? No, before that. There's a number we forgot. Yeah, it had to find n, right? So it would ask itself, okay, I have a pile of numbers here. How many of them are there? Right? So if you're a computer programmer, you're going to design an app. Right? You have to figure out the steps to tell the computer that you need to compute a median by doing this. So the very first thing you should do is count how many numbers are in the pile. That would tell you which equation to use, median for odd or median for even. Then you're going to sort them all, and you're going to use that equation of n to figure out which ones to look at. If it's a median of odd, you just have to identify which one is in the middle, which single number is in the middle. If it's median even, you've got to identify the two numbers in between the middle and then take the average of that. So what we're doing is, and this is how you learn statistics, we're going to learn it in the sense of the routine. Right? Bucket on the floor. There's a routine in place that gets us to the right answer every single time. It's repetitive. And that's why you have to create an equation for something like find the number in the middle of these 7 numbers. Right? Even with that, we had to apply a routine. First step, put them in order. Second step, count them. 1, 2, 3, 4, 5, 6, 7. N equals 7. What is 7? Is 7 odd or even? It's odd. 7 plus 1 is 8, divided by 2 is 4. I will find the median if I order them and then look at the fourth observation. Done. Routine. All bucket on the floor. Identify what the routine is, understand the routine, that'll get you to your answer. All right, so the last one, the mean, which we've already used because we need to understand the mean when you do a median. Now, you will see the mean represented a number of different ways in various textbooks. And now we're starting to really get into this idea of routine processing. And when we're creating the mean, this is the first time in most statistics books, including the one that I've assigned, that we start using that statistics word. Because the mean itself is a statistic. I'm not saying that the mode's not, I'm not saying that the median's not, but this is the one where we make that transition, where we start to think about having numbers represent larger data sets. And also we're getting into the hats. So we're starting to take letters and make them more complicated by putting, this is actually a bar. I'm sorry, I misspoke. That's a bar. So how do you say that? Do you say X with a line over it? No, that's X bar. And the letters that you use can actually represent other things. So this is, and most commonly for X bar, is actually known as a sample mean. Okay. Told you today was the last easy day. Because again, the math you've all had since high school. But now we're starting to think about this as we're creating numbers to represent something more than just what we observe. Because now we're going to start to make generalizations from the statistics that we get. And we started this last class, right? Remember the last class where I screwed up? I didn't have my example prepared. And I said, all right, well, let's think of why people might think of Hillary Clinton differently. And one of the ones that we came to was gender. Men and women might have different feelings towards Hillary Clinton. The theory, popular in gender politics, is known as representation theory, and that's you have warmer feelings towards people that look like yourself. And if you take that idea, you can apply it in lots of different social situations. Think of the lunchroom in middle school. Think of club recruitment day on Prince Lawn. What do? You walk around and you look for people that are like you. And those are the people you talk to. Okay? Can it work in politics as well? Absolutely. You can do it based upon race or gender. There are examples of men who marry women but take the woman's last name because it's better for politics. All right, I'm a Wood. Right? You can't get any blander than Wood except for maybe Smith. I'll give you Smith. But Wood is just so plain. Now, my wife was a Bauman. Does anybody know what ethnicity Bauman is? It's German. Okay? And if she was really German, there'd be 2 N's at the end of it. Even if I wanted to represent a community that is German, well, I would do a lot better if I took my wife's last name. If you're in Chicago and your last name is Wood, and you're marrying a Sidorsky, you take the Sidorsky name. Why? So you can get elected in that Polish neighborhood. In 2008, there was a primary in the Democratic primary, and there were two candidates. There was a state judge who I think was retired and was kind of in private practice. Vic, I can't remember Vic's last name. And he ran against another guy by the name of Alvin Green. Alvin Green was a retired, I guess, not really retired, is probably a discharged veteran who was in college at the time. He was finishing up his bachelor's in political science from USC. He was currently unemployed. He was living in his parents' basement, because that happens in real life. And he took his discharge money from the Army and he spent like $10,000 to register as a candidate for the U.S. Senate in the Democratic primary. He raised no money. He did no campaigning. He was just a name on the ballot. He won the election. Why? Well, he had a last name of Green. Green with an E is a common way that African Americans in South Carolina have a last name. And that was the theory. We can explain that outcome because of representational politics. Even though nobody knew who Alvin Green was, we could get from his name what he looked like, and therefore people actually voted for him just based upon his last name, which was a proxy for race. So that stuff happens. So when we are exploring data, and you might think, oh, well, I really shouldn't do this, right? Because this is sexist. This is saying that people are judging their support for another candidate based upon that candidate's gender. That's sexist. Yeah, it absolutely is. Right? It doesn't have to be a bad thing. We just have to recognize that it exists. So the example that I gave last class was, well, let's look at gender. And then I didn't have the full data set, and I had to find the gender variable, and I said, we're running out of time, I'll do it next class. So here we are. I ran it last night. Let's take the data set and split it into male and female. So I kept all the males, and I said, give me the summary of Hillary Clinton's feeling thermometer. The average score for men was 54.26. All right. And then bucket on the floor, I redid the process for women. I reopened the data set. I kept the female observations, and I said, give me the average. The average score for females was 60.65. So if we have males, females, this is HRC. Males was 54 point, I like two significant figures, so I'm going to call that 27. Females were 60.65. Okay, this is our little cross tab. We have two variables. We have gender and we have feeling thermometer. Is there a difference between men and women in their viewpoints of Hillary Clinton? I see lots of heads nodding. No. What is there a difference in? Because I said, is there a difference between men and women in their viewpoints of Hillary Clinton? And you all looked at the numbers and said yes. But that's not right. What is there a difference in?
Gender.
No. Nope. What do you mean? You're half right, but you went wrong on me. What do you think? What are you focusing on? Let's get focused on the right part. So it's not the fact that there were more men or women in the survey. What are you looking at?
I'm looking under ODS, I guess.
So the number of observations. So there were 1,300 women and 1,000 men. So you're saying that there's a difference between the two, and therefore, what? No, the mean's different because of the 1,324 women, their average score was 60, whereas of the 999 men, the men's average score was 54. Okay? So the fact that there's more women in the sample does not necessarily mean that that's why the score is higher, because I took the average. The average divides by n, therefore controls for that. What is it about this difference that we need to be careful about? Because I made a claim, I'll make another claim. Women are more likely, or let me rephrase that. Women like Hillary Clinton more than men do. Why is that wrong? It's not what? It's not all because? Okay, so you're saying that there's variability in whether or not women like Hillary Clinton. What evidence do you have for that? All right, so we know that the maximum is 100. I really should have dropped the not applicables, but all right, we know that there's a range of value from 0 to 100. So that is not the case for every individual. What Alexis raised is known as the ecological fallacy, where you take descriptions of groups and apply them to individuals. What do we also call that in common language, where you ascribe an individual a trait that you think a group has? Yeah, it's a stereotype, right? You know, all blank people do Y. And you're like, really? Because I'm blank, and I've never done Y in my life. Okay? It's a microaggression. All right. Somebody's had a training over the summer. All right, so let's think about that. Right? So on the one hand, Alexis is saying, well, you made a conclusion that at the individual level might not be true, right? Because Alexis might hate Hillary Clinton and Ben might love Hillary Clinton. And Ben's 100 and she's a 0, and I just said women have higher scores towards Hillary Clinton, right? So that's known as the ecological fallacy, or what we commonly refer to as a stereotype. That's one way in which we have to be careful about how we use the language of describing what we have found. Okay? So you would say women as a group are like Hillary Clinton more than men as a group. So that way we're not pointing at individuals. All right? There's one other reason why that statement that I made was a little too big. Does anybody remember? Women like Hillary Clinton more than men.
It's only 6 points difference, and the standard deviation on it is pretty big. I'm not sure if we're going to that part of it.
Oh, that's next week's stuff. I haven't taught you that. We're getting there. Jake said, well, there's a standard deviation. No, I haven't told you what that means yet. The only thing that I've explained to you as a statistic are observations and mean. So let's focus on that observation, which is where I thought we were going with your first comment, right? There's something about those observations.
It's small.
What do you mean it's small?
Out of the entire 300+ million people in America, we're just only polling 1,300 women in that.
Right. So the argument can be made that 2306, that the numbers that we derive from the 2306, what we're trying to do is we're trying to represent $330 million people. Okay. have we asked all 330 million people in the United States how they felt about Hillary Clinton? No. What we have is a sample mean. Okay? We have a sample. These distinctions are going to be important as we move through the course. Because, again, I can teach my 7-year-old to calculate a mean. But what I'm going to have a harder time doing, and why we're doing this at the college level, is to understand what that number actually represents relative to the population. So, time to light a candle and stare at it for a while. All right, let's think about this. What we have is 2,306 people. We have their viewpoints. We can then classify them down even further to 1,000 men and 1,300 women. What we have is a sample from the larger population. When mathematicians talk about populations, they also talk about things such as a universe, or, to get really high, truth, or true. I guess true would probably be a better word. Because let's say we could, using technology, maybe some brain implants, I don't know, maybe our alien invaders can do this, get every single living person's viewpoint in an instant, right? That would be the population mean. Every single person represents the population. But we don't currently have the technology to do that, right? And how long would it take to do a telephone survey of every single American? Even if we narrowed it down, voting age, 18 or higher, and the amount of time that it would take to do that survey, people would die and other people would turn 18. So then we're sort of constantly adding more and subtracting people. It would take that long. We try to do that in the United States. When do we try to talk to every single person in the United States? We do it every 10 years. And now we don't even really need to talk to you. We just want to know where you are. All right? We send a questionnaire to a house address and we say, hey, how many people are in the house? 4? Okay, tell me about them. And that's it. Right? We send the, there's a position, it's known as an enumerator. I was a census enumerator in the year 2000. You know what I did? I went to homeless shelters and tried to count people. And at first it was, excuse me, sir, I know you're eating your free hot breakfast, but can you tell me your name? And if I got a name, can you tell me about where you live? Oh, sorry, awkward. Just give me a city, or maybe a street vicinity that you usually are around. Okay, thank you. And then gauging upon how well they could answer your questions. So has anybody else already counted you? Right? And hopefully they're honest, because if you don't want to double count people. Right? So we do this every 10 years, and we take years preparing for the next one. And that's just a count. That's just to find n. Right? That's just to find n. So it's really, really hard. The census proves that. We can't do that. So instead, what statistics does is we hope that the math works out in such a way that we can use samples to tell us information about populations. What we have to do, though, is we can never forget that we are dealing with samples. And so when we make claims like women are more likely to support Hillary Clinton than men, or I guess, women think Hillary Clinton is more favorable than men, or whatever, we have to recognize that we're actually talking about a sample. And because we're talking about a sample, we can't ever know truth, but we can use probability theory to let us know an approximation of the truth. What do we call it when we approximate the truth? What do you have to have? What does it require of you to approximate truth? Okay. So if I were to show you some numbers and give you data and tell you this is how people feel about Hillary Clinton, you'd be okay with that, even though it's only 2,300 out of 330 million. What else do you need? It's not a math answer. It's more of a logic answer. What else do you need to put probability in so that we can make conclusions, approximate truth? Ben?
And that's for like rationally justified.
Okay, we're getting closer. What do you mean by rationally justify?
Like it has to make sense. Like you can't, if you were to do like survey of 30 people that live in one neighborhood and it happens to be a predominantly Democratic neighborhood, and you can't justify that then the larger population is going to support her more so than the other candidates.
Okay, so what Ben just described was potentially crafting a biased sample, right? You go to a neighborhood or a cul-de-sac or a trailer park or whatever, and you're basically, what Ben is saying is what you've done is selected a very small population that is probably the same. All right. So how can we, again, have faith in the data?
You have to distribute the survey throughout different areas based on socioeconomic.
All right, so now he's talking about a process. Okay, Ben is talking about there's this process out there, right? If you're going to do something on a sample, you have to do it in a blank way. What's the word we usually use to say, trust me, I'm doing this right? It's the blank way. The right way. I like the S's. We're getting closer. Scientific, right? Okay. So we're getting closer, right? What do you have to approximate the truth? Well, we have to do it in a convincing way, right? Because I have to convince you that 2,300 can represent 330 million. Now, whenever I teach polling in like POLI 201, I always tell the soup story. Anybody ever hear my soup story before? Jake, you have? All right, Jake, let's do this quickly. Jake, I give you a bowl of soup. You're going to eat it. What's the first thing you should do? It's not hot. I'm not going to burn you. So you're not going to blow on it. It's of appropriate temperature. Bowl of soup and a spoon. What's the first thing you do? Pick up a spoon. All right, he's really bucket on the floor here. All right. What's the next thing you do? You're doing it wrong. You learned nothing from me last class. This was like a thing. You're supposed to remember this. Tell Jake what he did wrong. He's got a soup spoon in his hand, and he just wants to go ahead and eat that soup. What should he do first? No. Say your blessing. Yeah. What do you do? How do you eat soup? None of you guys have all failed the test on how to eat soup. The soup's in the bowl. You got a spoon in your hand. You're ready to go. What's the first thing you should do? Yes, you put it in there, but then what? No. You don't scoop it. You. Why do you stir soup before you eat it? To mix it up. No, you don't. You haven't made soup in your life. I can't believe this. You guys are college students at a university and you don't know how to eat soup. Don't eat soup, please. All right? The first thing you do when you eat soup, after you do all the stupid stuff like blow on it and, you just stir it. Why? Because you want to mix all the ingredients up. Yes, you do. Because if you don't, what happens? You're eating chicken noodle soup, you put your spoon in, what do you get that first little? You get the broth. You don't get the chicken or the noodle. You got to shake the soup up. If you're sipping it, I'm going to sip my soup. No, you're not. You got a big old spoon. You need to stir it up because all the good stuff sinks to the bottom. There's a process in place for eating soup. There's a process in place for doing math, doing statistics. We got to have faith in our process. So what is required in order to use an approximation of the truth to represent the universe? Two things: belief in a process. Sometimes they do. Sometimes people guess. That's why I keep doing this. Right? Sometimes people can read my mind. I know you can. You just don't want to use your power all too frequently. So you hide it and you act like you never know what I'm trying to say. You need belief in a process. And what we're going to do is start thinking about processes to analyze information in a probabilistic way. Right? Probability theory. And the belief is, generally speaking, that when we observe an event happening and we see that event happening over and over and over again, we need to know, is that same event happening in the ones that we don't see? So for the 1,000 men, right, and we asked the 1,000 men the question about Hillary Clinton, can we believe that the other 329,999,000 men would do the exact same thing or have the same belief? Right? That's having faith in probability theory, that what we don't observe is the same as what we do observe. So we have to make sure that we do this in a scientific manner.